to commence en anglais, and during the question and answer period, if we can try. Thank you very much for coming. Just to say, I started this is a part of a project that I actually started with Jean. A few years ago, we had a conference here on the economy of nature, and Jean was working on botanical arithmetic of Darwin, and I picked up on these. And the reason why I don't put us as co-authors is very simple. I think by now he would disagree with absolutely everything I say. So it's sort of the core came together, and now it's not at all what he would expect. The other thing I want to think too is that we have a little group here of faculty called Postscriptum, and we go through drafts of things, and I benefited greatly by a run through the Postscriptum review process. So I thank everybody that helped me there. I wanted to start I wanted to start with a philosophical question. And the philosophical question concerns something that I don't know if you're very familiar with, but a biologist by the name of Ernst Mayr, who is also a popularizer of biology, evolutionary biology, once remarked that one of the great things that Darwin contributed to biology is that he brought population thinking into biology. Okay? And of course, as you can imagine, philosophers and historians, mostly philosophers, have spent quite a lot of ink, spilled a lot of ink trying to figure out what this means. And there seems to be at least two senses, right? One in which it seems to be that Darwin did very well, and the other one not so well. The part that Ernst Mayr, and Ernst Mayr is a little bit vague on which part that he means, but one of the senses of population thinking is a kind of, I'll call it a metaphysical sense of population thinking, whereby what Darwin brought to biology is this idea of destroying the idea that species are essentially defined, and they're much more sort of a population variational kind of concept, okay? And here, Darwin did very well. So Darwin's theory of speciation is an instance of this kind of rejection of essentialist metaphysical thinking in favor of another kind. But there's another sense of population thinking, which let me call it methodological, right? And this methodological is a way to understand how you get something like evolutionary trends, right, understood as a kind of high-level effect that belie individual differences, right? And one of the things you might think about with this kind of thinking is that the sort of ultimate way of thinking about how to understand the relationship between higher-order effect and the individuals that make up that effect is through statistics, okay? So if the claim is that Darwin introduced statistics to evolutionary biology, that he didn't do so well, right? So what you hear is that Darwin was, at the very best, made evolution ripe for statistical analysis, but he wasn't a population thinker in the sense that he introduced statistics to evolutionary biology, and that's the claim that's often made. And why wasn't he? Why are you not surprised that I said that Darwin didn't introduce statistics? Probably because you adhere to the dum-dum view of Darwin, and that is that he was not mathematical. He had a non-statistical mind. Apparently, two of his sons had claimed this, right? So he just wasn't good at math, is what the claim is. Okay. And this is the topic of this talk today. I want to dispel it somewhat. I am not going to tell you that Darwin is a brilliant statistical thinker. I'm not going to tell you that he contributed to probabilistic theorems. I'm not going to say anything like that. I'm not going to make him a brilliant mathematician. His views, his ways of doing statistical analysis were, even to that day, rather primitive. But what I find remarkable, and this is why I started this project, is when you're digging into his notebooks and some of his correspondence, out emerges a character who used simple statistical methods in very, very clever ways. In fact, I would argue, and I am arguing in a book with the same title, that Darwin was able to use statistics in at least three senses, right? So let me be a little bit more clear before I go on what I mean by use of statistics. I mean looking at patterns, these high-level patterns like evolution, from the viewpoint of statistical data, and using models, mostly probabilistic models, to analyze them, to predict their direction, or to even explain them. Okay? And so I want to argue that Darwin used this kind of statistical thinking in three ways. He used it to detect ensemble-level patterns emerging from individual variations. He uses a detection device. He used it for hypothesis testing and even explanation. Okay? And what I wanted to do is, I've uncovered a few cases like this, but I want to show you two of them. Okay? Two cases. Right. Here are the two cases I'm going to talk about. I want to talk about one case in which he used statistics for this first two, for detections of ensemble level. By the way, the good news is I'll make it more clear as I show you the examples, what that means to use it for detection, and also for hypothesis testing, and I will point this out. So part of this is a history lesson to celebrate Darwin, right, to show that he actually did make contributions to biology from a statistical point of view. But it also is to make more clarity, the philosophical question of clarity, and what a statistical method really is, especially during the 19th century. Okay? So the two cases that I hope to get through, if I have time, is one comes from chapter 2 in The Origin of Species, and it's a famous argument that he provides, where he claims that varieties are so if you have a species and you have a variety, it's going to be a type that's different than the species, not different enough to become its own species, but it's also regularly different. And what he wants to argue in chapter 2 famously, that varieties are incipient species. In a sense, I'm going to argue that's actually quite startling. He's going to be arguing that he can detect speciation in action. Okay, so I'm going to make a big deal of that. Okay, so that's the first case. I'll talk to you about. And then the second one is quite surprising. I found a second kind of case of outbreak of statistical thinking in a paper that's very obscure, written as a letter to Nature in 1874. And the topic is on, the title is something like, well, anyway, the topic is about rudimentary characters in certain kinds of barnacles. It's really about rudimentary characters overall. So the barnacles, the issue is that on some barnacles, the females are very large, and where are the males? Well, they're really been reduced to little detached or attached penises, basically, on the females. So they've kind of evolved such that they're almost diminished completely. Okay? And so what he wanted to do in this letter is he wanted to give an evolutionary explanation for how the evolution of rudimentary characters, how they become so diminished. Okay? And I think this is a remarkable thing that needs to be a little bit analyzed more, and so I'm going to introduce it to you. Okay? Okay, you ready for this? You want to let's have some fun. Let's talk about this. I think this is quite impressive. Right? So I'm going to take a look at the first case here. Just go right into it, where this is from his chapter 2 in The Origin of Species. What's interesting here is that the argument's going to go into two steps. The first step is Darwin's going to present to you some facts that he drew from statistical analyses, of which he does not publish. He makes claims that he might eventually publish it for people, but he never does. But you can find them in the notebooks and some of the letters, especially the notebooks. In fact, when you look at the notebooks, this is what Jean told me about, is that you see reams and reams of these things. Okay? That's the first part. He's going to state some statistical facts that he drew from his analyses. And then he's going to make an argument for natural selection on the basis of natural selection is the best explanation for those statistical facts. Okay? So I'm going to follow along in two parts, and I will abbreviate massively from them, because actually, even though the part in chapter 2 is very short, it's quite intricate. So I'm going to cut corners and make it cartoonish so I can present it to you. Okay? So let's do the first part of it. Okay? This is what Darwin says in chapter 2. He says, I thought that some interesting results might be obtained in regard to the nature and relations of the species, which vary most, by tabulating all the varieties in several well-worked floras. Okay? And then, of course, he doesn't publish it. But he does, he gives us a summary of this is a summary of some of the things that he discovered. And what I'm going to do is, I'm going to get you used to some of the terminology, and then I'm going to show you how he derived this one. Okay, how he came to derive this fact. Okay? So first of all, what is he doing? What is he tabulating? Well, at the time, there were volumes of these zoological surveys, which would catalog certain kinds of plants. He was mostly interested in plants, and sometimes insect species, or insects, and so forth. And he took these massive volumes, or maybe they're not all massive, but anyway, and he would try to look at certain relationships between species. And he's mostly interested in 3 levels, okay? So he's interested in the genus, and then the species is underneath, and then he's interested in varieties, okay? I will call, I'll be mostly saying genera, which is, I think, the plural of genus, okay? And he's going to be interested in seeing if he can find interesting patterns with regards to the frequency of varieties to species and species to genera. And it's going to be a tongue twister, I warn you, okay? I know that also that this is a French audience mostly. I'll try to go slow, but it is a tongue twister. Philippe presented my paper in this postscriptum, and even in French it was like a tongue twister, so I have to apologize, but you'll get the hang of it, okay? Another piece of terminology I want to tell you is, as we go through this, here are the 3 facts. One is dominant species. Dominant, he has a specific definition. Dominant means the species that is found most diffuse across a land, but also within a land, it's most diffuse inside the land and most numerous. Okay, so those are dominant species. He claims from his analyses that dominant species present varieties. You remember what those are? This is crucial. This is going to be the variations that aren't enough, they're not different enough to form their own species. They present varieties more often than non-dominant species. Okay? That's the first thing he's going to show. The second thing he says he shows is that dominant species are most commonly found in large genera than in small genera. And by large genera, that means genera that have a whole bunch of species. More species surrounding or associated with them than small. Okay? And the third one is the part I'm going to focus on and how he demonstrated this. Species of large genera more often present varieties than species of small genera. Okay? One last piece of terminology. Where is he getting this information about varieties, genera, and species? It's going to be those that are marked in the books. Okay, so he's not determining whether this is a species or a different species. He's using the expertise of the field guides. Okay, authors such as Asa Gray in Massachusetts. I don't remember the other ones all of a sudden. Anyway, a bunch of those like that. Okay. Okay. So. What I'm proposing here is I want to show you how he's going to, remember, so let me just make sure we're not lost here. I want to present his argument in he presents an argument in 2 steps. One, he reports what he finds from his statistical data, and that's what we're going to get excited about. And you will, I think you'll like it, okay? And then the second, he's going to use that data as an inference to the best explanation for natural selection, okay? And I'm still on step 1. And instead of showing you each of those summaries, 1, 2, and 3, I'm going to focus on this one, that he claims that he found in his tabulations, species of large genera more often present varieties than species of small genera. And I'm going to present this chart and explain it, and we'll see where the fun comes from. Okay? The first part, so you get 2 parts again, the first part is quite not that unusual what he does. There's a little bit of a twist, but he's doing what's called botanical arithmetic. Okay? It's quite well known. He learned it in college, probably from Henslow. It doesn't matter. It wasn't anything terribly unique. Okay? But his little twist is this. By the way, for historians in the group, Jean will be yelling at me because I'm making historical error. But actually, if you look through the development of his views, he has 2 ways of doing the calculations. He did it one way. Someone pointed out an error. That person's name is Lubbock, his neighbor, and then he had to redo his calculations. I'm going to tell you the post-Lubbock calculations. Okay? So, right, I know people are going to jump down my throat if I didn't say that. Okay? So the way he did it is that he wants to define large genera as containing 4 or more species. And again, whether they contain 4 or more species depends upon the catalog. He's not going to make the determination. This is his a priori assumptions. Small genera are going to be the ones that contain 3 or fewer species. Okay? And then he's going to look at, these are the numbers of varieties, and he's going to look at number of species. Here, this represents the number of species, okay, the number of varieties, the number of species of a large genera, and he's looking at 339. So that is, of a certain kind of plant, he found 339 species that are associated with large genera, 4 or more, okay? And he found roughly the same, 323 species that belong to the small genera. Got it? Mm-hmm. Okay, good. Now the second part. This is the number of species presenting at least one variety. Okay? So 51 species present one or more varieties that come from large genera with 4 or more. Okay? Got it. And then 37 is the number of species presenting at least one variety from the small genera. Okay? And there, right, remember what he wants to show is species of large genera more often present varieties than species of small genera. It would be silly, easy, but wrong to just simply say, well, I just showed it because 51 is greater than 37. Okay? That would be boring if that's what he did. Okay? Do you see right, how we established it? Okay, good. I just want to make sure nobody's lost here. Okay? So, why is this silly and boring and probably wrong? Because there's an auxiliary assumption attached to it. Okay? So the assumption that what he wants to demonstrate is that these numbers aren't, remember, this is supposed to be an explanation for natural selection. That is, it's supposed to be evidence of natural selection. Okay? So what he needs to do is he needs to associate some meaning to those numbers in relation to the ability to create species. Okay? So the assumption is, it would work if the assumption is correct, that 51 is greater than 37 is a reflection of a greater reproductive tendencies of large over small genera. You see that? So in other words, it's supposed to be meaningful. Right? This is supposed to be an indication about large genera, that they're more productive. Okay? The more general view is that large genera are ones that are healthy and growing. Okay? And small genera are dying off. Their species are becoming more and more extinct. Okay? But notice, by the way, you might have a small genera that's small because it's growing and he just caught the snapshot at the wrong time. Or it might be one that's dying, right? How do you know from just a snapshot, right? And then, if that's the case, how do you know this reflects reproductive tendencies? It shows whether it's a healthy genre, that is, this small one is actually healthy and it's growing, or is it a dying one? How can you tell? I think if I had a lot of time and just studied this case, I would just go around the room and see how you would solve the problem. Okay? Unfortunately, it would be silly to do this because we have a statistician in the room and he would figure this out and so forth, right? But anyway, it's kind of clever. Like, how would you figure this out? What Darwin conceived of, again, remember, the whole point of this is to show you that this is simple, but has really profound implications. Okay? So, what he does is he devised what I think is a counterfactual test. And he asked the question, how many species presenting varieties should small genera have? How many species presenting small varieties should small genera have if it had the productive tendencies of a large one? Because remember, we want to know, is this a dying genera or is this a larger one? So he's asked the counterfactual question. What would this number be if it were a very healthy one? What's a healthy one? Well, we know these are healthy. So what would it be if it's acting like this? Okay? And then he says, I can answer that question. Are you following this? Because you're getting, I'm excited. I hope you are too. This is really cool. Okay? Here's how he suggests that we answer this question. He pulls out a very simple arithmetic trick called the rule of 3. Does anybody know the rule of 3? Okay? What it is that we have an x, an unknown value, and we have proportions. The x unknown value is how many species presenting at least varieties would would this be if this one is reproductively robust as a large genera? Okay? And so this is what he did. I wrote it on the board because I don't know how to do this. Okay? So I wrote it on the board. So what you do is, remember, here's the ratios. Make sure I get this right. So here's the proportions. 339 to 322. We're going to keep that proportions like this. And the 339 produced 51. Did I get that right? Am I copying right? And what he wants to know is this x value. Okay? And the rule of 3 is very, very simple. I never heard of it until I read Stephen Stigler's book on this. But it's this. He's going to do a cross multiplication. Okay? And then we're going to find out what the value is. So here it's 339. I'm just showing you how simple this is. X, tell me if I make a mistake. 323 times 51. I don't want to go to the next round. If you get a calculator, some big number, 16,000, blah, blah. And then we're going to divide both sides of the equation by 339. And you're going to get, well, you didn't get the answer exactly right, but you're going to get 48.59 if you drop the 9 anyway. You get about 48.5. Okay? And in fact, so there, I have it there. And now here's what's significant. He says, look, this number is smaller than what it should be. Okay? And here's what he writes in his note. It's actually in a letter to a friend. Okay, I think it's Hooker, I think is his friend, who did one of the surveys. If small genera had the reproductive tendencies of large, they ought to have had 48.5 species presenting varieties. So that is what I wanted to show. Okay? What did he want to show? He wanted to show that this is indicative of species or genera that's dying off. Okay? From this sort of calculation. I'm pausing here because that's kind of cool, isn't it? He used a simple arithmetic thing to do a counterfactual test. Quite sophisticated stuff. Okay? Okay, but I've kind of lost sight. What were we supposed to prove? They're just so impressed. Okay? He wanted to prove that. Okay? He wanted to prove that species of large genera more often present varieties than species of small genera. And now he's comfortable that he's shown this. This was, by the way, just one example of many, many, many calculations, which he didn't do, by the way. He hired somebody to do it, a sort of school teacher. So the handwriting is from this other person. Okay? So now, that's it. So I wanted to show you, right? So there's two steps of this argument. One is he was going to do the statistical representation. Sorry, the facts that he derived out of the statistical analyses. And now he's going to do an argument. Okay? But what I want to do is I've demonstrated something already. I've demonstrated that his analysis of an argument, or you'll see his crucial part of his argument, is driven by statistical considerations. And by the way, remember I was quite vague on what that means? Now we kind of get a better sense of what I mean by statistical considerations. What he's done is he's done arithmetic studies about the relationship between frequencies that he observes in classes of organisms. Okay? Quite sophisticated stuff in some sense. All right, let me go ahead and do the argument now. Remember, the argument that he's going to do is going to be an inference to best explanation. So what best explains those facts? I'll just isolate it to this one. What best explains the relationship that he sees over and over again? He wants to establish this as quite a rule. Species of large genera more often present varieties than species of small genera. He says, well, special creation can't explain this. Because if these were just simply acts of special creation, if they were put there for certain reasons, there'd be no apparent reason why more varieties should occur in a group having many species than then having few. So that sort of asymmetry isn't well explained by a special creation. He says, let's think of it kind of like an analogy. Let's think of the situation kind of like when you're out in nature and you see many large trees grow. Where many large trees grow, you find a bunch of saplings. How would you explain that? Okay. Well, it seems to be that that if you just simply say is that they were independently put there, that is, the saplings were distributed by one, then you're missing why the clustering. Okay. So that part needs to be explained. And the special creation, just the idea that they were independently created, doesn't explain the clustering. But if you suppose evolution by natural selection, then you might explain the clusterings. And here's how the explanation would go in a cartoon version. Is that when I see the clusterings around certain genre, what I'm doing is I'm looking at a snapshot of a very productive system. Okay? So why is this genre so large? Why are those trees so large? Because, as the explanation goes, in the past, those trees had the ability to win the struggle in the environmental conditions that they're in, and their production is the bigger trees. Okay? And then he needs to make an assumption. He makes an assumption that past conditions of the soil and the conditions and so forth remain for the future, a kind of principle of uniformity of nature. If you help yourself to that, then you can assume then, or you can use that same sort of explanation to explain what's going on, why there are clusters of saplings around those large trees. The same conditions that favored those large trees remain, and what you're seeing is their productive output. Okay? It's showing the winners again. Okay? That's his argument for how he can explain these sorts of large facts. Okay? Alright, let's pause. I mean, if I finish, I think this is cool. Because I don't think people realize, and I did, it was kind of a eureka moment, you realize how interesting this is. I don't know, maybe it's I misread Darwin for so long. I always thought Darwin had a really big task, that he had to show natural selection in action without any direct evidence. Right? Wasn't that the thing that we sort of associated? There's no proof that selection actually, the speciation is actually occurring in nature by natural selection. But I don't think so anymore. I think this is what he did. He tried to show that he had evidence of speciation in action. And he used his statistical analysis to show that. I think that's impressive. And it might, maybe it was my change in the way I thought about origin of species and its challenge. But clearly, I think that's the role that it's supposed to play. Okay? That's really cool, I think, anyway. Okay, let's sum up. And then I'll go to the second case, if you'd like me to. Yeah? I don't remember how. Is that okay? It might go quicker, it might not. It depends upon how much you understand what I'm going to talk about, but okay, we'll see. What I've just done is I've tried to demonstrate that Darwin used statistics, sort of statistical thinking in the origin of species. And in three senses I was trying to argue. One, he used it to detect ensemble level patterns. He used the statistical summaries to do that. You saw that, right? That data wasn't there. He had to tabulate it. And then second, he used it for hypothesis testing. This is what he did for hypothesis testing, right? And that's that counterfactual test. So he used these kinds of arithmetic manipulations of this to determine counterfactual conditions, to try to confirm a certain hypothesis. Okay? All right. But now, what I want to do is the second case, is I want to show him using statistics for explanation. And this, to me, is really cool, because the thing I'm most interested in is the difference between Darwin's theory of natural selection. Some people heard this today, right? Some students here heard this today, and the modern synthesis. And one of the big pet projects I have is to destroy that idea that the modern synthesis is a union of Darwin's natural selection with the Mendelian inheritance. I think it's like Voltaire said of the Holy Roman Empire, it's neither holy nor Roman nor an empire. I think that the modern synthesis is not Darwin's theory, it's not preserved. Okay? So what I find very interesting here is this is going to contradict me greatly. Okay? And that made me stall like another year for writing my book. But anyway. So let's get on with it, okay? What I want to do is the second case, and I want to show you how Darwin used statistics, not very sophisticated, but clever ways. Remember the case I told you. Here it is. Here's the title. On the males and complementary males of certain cirripedes and on rudimentary structures. And what he's going to do is he is going to actually give a statistical model to do this explanation for how it's possible, a kind of story to tell, how it's possible that rudimentary characters, that is, characters that shrink in their sort of, that will shrink in size especially, how evolution could cause this. Okay? And he's not going to do it the way Do you remember how I just did the evolutionary explanation before? I talked about winning the struggle for existence, and there's that kind of tendencies of how... He's not going to use that language at all. Okay? He's going to use the language that refer without actually saying a mathematical or probabilistic equation. Okay? And so what he's going to do in this, and I need to explain this, is he's going to apply what's called the statistical law of variation. Terminology's a nightmare here. Oh my God. Is this his language? Is this, well, it gets worse than you think, and I'll show you why. But what I'm going to show you is I'm going to show you what the law of variation is. And he's going to use it to actually model the evolutionary process. Here it is. Okay? The law of variation is, given certain kinds of conditions, okay, the conditions are quite simple, that you have numerous individuals in a trial, a chance trial, and whose outcomes are independent of each other. That is, their probabilistic outcomes are independent of each other. And when you aggregate those, you're going to, and you aggregate those, and then you plot the frequency of various types, you're going to get a bell-shaped curve. I'll explain it again in a minute, but that's what he's going to refer to. That's the law of variation that he's referring to. Okay? And he's going to use that to explain evolution of rudimentary character. You ready? You ready for it? Okay. Right. First, something I'm going to tell you. I actually published this a long time ago, and some colleagues of mine, an analysis of that paper, and some colleagues of mine also published and said, Andre got it wrong, but that's okay. And I was looking back over it, and I realized I didn't really understand it the first time when I published it. I thought it was nothing significant. Okay? And then I spent 2 months reading and reading and reading this thing, and it's incredibly opaque, and I'm about to give up. Oh, hell, I'll just give it to Steve, who may can figure it out for me, right, as an expert on history of statistics. But what then I came across, just kind of by accident, others may have known about this, but I didn't. I noticed that the problem wasn't me, it was Darwin. He screwed it up. It was so opaque. Okay? How did I discover this? Because a few weeks later, in October 4th, 1873, in Nature, comes an addendum to the letter by his son, George Darwin, who was pretty good at statistics and mathematics. And here's what George says about Papa Darwin. My father finds that in his letter, published in your number, September 25, he did not give with sufficient clearness his it's not me. His hypothetical explanation of how useless organs might diminish and ultimately disappear. I therefore now send you, with his approval, the following further explanation of his meaning. If I could tell you a quick little story. I also found a letter between George and Papa. Okay, and what it is George sends Papa this addendum and says, here, you should publish this in Nature because you screwed it up, Dad. This is better. And George writes back and says, thank you. But look, I didn't mean much of this. This was just hypothetical. It was just sort of playing. So it's okay. I don't really want to publish it. And you go ahead and do it. And don't put my name associated with it. Put your own name. Okay, I don't know if he was embarrassed by this or he just wanted his son to do it. Okay, so what I'm going to do, one thing I don't know why, but George stops talking about penises and males and barnacles, and starts talking about, instead, horn sizes. Okay, so I'm going to switch the example too, if you don't mind. Okay. All right. But for me to do this explanation, I've got a kind of, if you've never heard of this sort of law of variation before, I've got a little bit of an uphill battle to climb. And what I'm going to do to help is I'm going to explain what I just did about the law of variation through a little device. Okay? A little device, again, historically this is a nightmare because it's really been created after this presentation, not too much after, a few years later, and it's by his cousin, Francis Galton. And so here it is, and actually this is a toy version. I forgot to bring mine to Paris. I have some, there's somebody who manufactures them, but I got a video of it. Okay? And before I run the little video, I want you to, it's hard to see, but I want you to see what this is. Okay? What this is it's a machine where I'm going to put this lead shot, you'll see it's going to move. We're going to pivot this way and that way. Actually, let me go ahead and do it. There we go. Okay, so this is lead shot. Okay? And when we turn it over, it's going to go down and hit pins. Okay? And the pins are arranged in a very particular way. Oops. Sorry. See, I get very excited about this stuff. Okay, so the pins are arranged like this. A particular pattern, which I guess is what's called a quincunx, which one of the theories is that it's derived from a way French gardens garden for maximizing the nutrients between the trees. But you also see the same patterns in fishing nets or the number 5 on a die. Okay? But here's the key of it.
No.
Huh?
Armies.
Sorry?
In armies, when you do, like, no?
Il y a qu'un cours, sinon les formations en 15 cours, c'est pas un truc de... C'est ça, ouais, ouais.
Je ne sais pas.
Roman army and maybe...
Oh, right. The sort of flanks of the Roman army. Yeah, that might be it too. That could be. I think there are many patterns. Fish nets have this pattern. But what's interesting for our sake is that whenever a little pellet drops, it's going to hit this, and then it's going to have a 50-50 chance, basically, of going one side or the other. Okay? And so once, let's say, it goes this side, once it encounters it, it's always going to encounter in the next level another pin. That's what's nice about the way it's arranged. And then you have another 50-50 shot. Okay? And so really what this is, actually, is just a kind of accumulation of coin flips. 50-50, okay? And what we're going to do is, what the representation of all these together, what's happened here is these are little chutes. Can you see that? So it can capture where it's going to fall after it goes through its array of pins. Okay? And these chutes will allow it to keep stable. But what you're doing is you're seeing the result of an aggregate effect of maybe many coin flips or many 50% chances. This is, I guess, would be called the binomial distribution. Okay? Right? Because it's a product of two different possible outcomes. Okay? So anyway, there's going to be a lot of slop here. Is the law of variation the normal distribution or the binomial? Let's just skip all that. Okay? But you see what's going on here? Now here's the point. Remember, I actually told it to you a little bit earlier, and let me try to say it again. And the idea is this, is if you have a process that's kind of like a set of trials, like coin flips or these trials that are aggregate quite a bit, and they're numerous, a whole bunch of them, and their outcome, where they fall, is independent of the others, then you will expect, in these cases, to get this bell-shaped curve. Okay? Notice it doesn't exactly get it. And, oops. It doesn't exactly get it. It's kind of close enough, right? Why? Well, it needs more numerous. By the way, there's another condition, right? It has to be bounded. It's not right. It has to make sure that there's nothing such that some of the outcomes could be way here and here. So there's going to be some sort of bounding condition as well. But you see this all over the place. Okay? Now, why is this called a law? All right. This is due to, maybe I shouldn't have introduced him, but this is who Darwin introduces in his version of the text. He's referring to an astronomer turned statistician named, or turned social scientist named Adolphe Quetelet, who's Belgian. And he came up with this law. And here's the law. It's not this, of course. This comes from, you can see this in De Moivre, you can see this in Laplace, and so forth, okay? Well, and probably Quetelet might have learned it from Laplace. Anyway, but this is not Quetelet's contribution. Quetelet's contribution is that this normal distribution, this distribution, bell-shaped curve, should be expected everywhere in nature. He basically, exaggerates quite a bit, but says that all characters in nature should be normal, or should be distributed by this. He didn't have much evidence, but here's some evidence. Okay, evidence of this distribution, this bell curve distribution, in data that's collected between American soldiers, French soldiers, and Belgian soldiers. Okay, and what we're doing is we're taking the numbers associated with some height. So this is the frequency of types, remember? Okay, and you'll notice that each one has, I love this chart, because actually you see the curve. Right, that's kind of I don't know if it's coincidence, it's just a beautiful representation of it. Okay, and so then, for Quetelet, he made a huge deal of this. The fact that the American soldiers have a higher mean than the French and the Belgians and so forth. He made a big deal of this, but that's not the part that we're going to be spending time on. He thought that this was characteristic of some essential features about American soldiers, French soldiers, and Belgian soldiers, okay? But what's significant for Darwin is this idea extrapolated by one or two cases. Scottish chest sizes might be distributed like that anyway. But it's true, you often see it in nature. Why, by the way? Why do you often see this bell-shaped curve in nature? Because lots of systems in nature have those minimal conditions. Okay, I'm planting something in you because I'm going to give a talk again here on March 30th, and I'm going to play a lot with this concept of minimal conditions for statistical explanations, okay? Right? So a lot of things in nature actually have those kinds of processes. You see this in apple sizes, you see this in the way they grow, and I mean tons and tons of applications. So lots of people use these kinds of bell-shaped curves, and this isn't the first time you heard of bell-shaped curves, even if you aren't a statistician, okay? Because they are quite popular in science. Okay, now we'll get to it. Is this enough preliminaries? Okay. I'm going to give you George Darwin's version, okay? And I'm going to do something extremely embarrassing. I don't know how to draw or to get nice-looking bell-shaped curves. And in fact, mine are going to be a disaster because they're actually not really bell-shaped curves because, well, you'll see. These are supposed to be limits. They're supposed to tail off. And so since I didn't know how to do it, I started spending hours and I said, the hell with it. I can just, just apologize and just show it to you. Pretend this is the normal, this is the distribution of bell shape. This is not at all, right? It should be sloped like this, okay? Do you mind? Okay. Yeah. I wanted to show you the parts. George did.
It's the logarithm of a normal distribution.
Is it logarithm? Okay. So they do cross the x-axis.
Oh, well, the log is a...
Right. Okay. But that's not what he was
a parabola. No,
okay.
That's not.
Yeah. Okay, very good. That's important, so I'll tell you why later. Okay, so here's George Darwin's version of Papa Darwin's explanation for how evolution might be the cause of the diminishing of the effect. Okay? There's 3 steps to the argument. First step. Suppose that the distribution, remember we're going to horn sizes, not penises. I guess don't want to be too prurient here. Horn sizes according to Quetelet's law of variation. So if I take a population of horn sizes among some cattle in a big field, full of them, you'll see the distribution of their horn size to be like this. Why? Because Quetelet said so, I suppose. Okay, but let's just assume it. Let's take a look at the second step. So this is the parent generation. They produce some babies. But they produce babies in a time in which their resources are very poor. Okay? And in this case, the resources are very poor for development, and that causes some of the horns to be stunted during growth. This is the babies, right? Okay. Now, what would be a representation of the frequency distribution of these stunted? Well, George says, let's suppose it would look like this. So here, I should have labeled, this is the original mean. So let me go back. This is the mean. It's not exactly center, it's hidden. Okay, there it is. He says 2 things will happen to the distribution curve, right? He's going to assume that the stunted growth occurs mostly on this side. That is, the ones that were pretty much on the small end anyway, and the rest were normal, okay? And he says what will happen is the distribution curve will shift down to a new mean, and the slope of one is going to be longer than the slope of the other, and this will be as asymmetrical to the old one. Okay? So that's the second step. Are you seeing how this is going to go? I mean, you already know how this is going to go. We're going to have a down step. Okay? Third step is selection. Okay? There's a twist to this. Selection, he says, will restore the bell-shaped curve. Okay? That is, this is what happens. You have stunted horns. These are normal. Okay? And these are actually larger than normal. Not much larger than the old normal, but some are. Okay? George says 2 possible conditions will lead to the same outcome. The same outcome will be the distribution curve, like you expect from Quetelet, just down one in the mean. Okay? What are these 2 conditions? So he says it's going to happen whether selection for horn size or not. Okay? Suppose, I don't remember exact words, something like, suppose it makes no difference to the struggle for existence, the horn size at all. Okay? Then what will happen is that you'll get random mating, he claims, and that random mating will just make this recalibrate, accept a different mean. I'm a little puzzled too. I don't understand why, but this is what he says. Okay? The second case in which selection, it matters. This horn size matters in this case. In that case, he says, well, these ones won't do so well. But notice that most of the mixing between individuals are going to be still around this kind of larger than the smaller ones. And if you get the sum of that mixing, you're still going to get the same sort of bell-shaped curve. Okay? I don't understand that. No, I don't. I think what he's doing is he's thinking about how Quetelet's law is true of every generation. Why? Don't know. Galton will invent that explanation decades later, okay, which is kind of cool in itself. Okay? But let's go back to what I wanted to prove to you. Cool, huh? Here's his argument, is that if you take the law of variation by Quetelet as a way to describe the distribution of characters, and you have poor environments, you're going to get this, it would be really cool if I could animate it. You're going to get step down, step down, step down, until you get them really, really small. Okay? That's how evolution explains the existence of rudimentary characters. Okay? That is super cool. 1873. The last edition of The Origin of Species is what, 69? Okay, this is years later. Why is that super cool? Independent of what I'm telling you in this lecture here. This is what we're used to hearing from Darwin. This is from The Origin of Species. The last couple paragraphs. It's interesting to contemplate an entangled bank and to reflect that these elaborately constructed forms, so different from each other and dependent on each other in so complex a manner, have all been produced by laws, natural laws. You think kind of Newtonian laws, acting all around us. These laws are growth and reproduction, inheritance, variability from direct and indirect action of conditions, and from use and disuse, and, most importantly, a ratio of increase is the Malthusian parameter, I hope you know what I'm talking about, so high as to lead to the struggle for life. This is how we're used to thinking of Darwin. It's a theory constructed out of laws. What we're used to thinking is, for population genetics, if you ever open a population genetics text, you're used to thinking of natural selection in terms of these models and these types of distributions. This is stuff that you would see in the 20th century, after 1920s, 1930s. You will see natural selection being represented this way, with these distribution curves and things like this. But notice what's happening is, I just gave you the 1873 version of Darwin that looks a lot more like this than it does his old self. Okay? There's really prescient here. Again, remember, I promised you not a brilliant mathematician. I didn't promise you that we can even understand his statistical reasoning. But it's done in very clever ways. Remember, I promised you that in my two cases that you would see Darwin using the statistical analyses two different ways to detect ensemble level patterns in hypothesis testing, that's case one, and a very different way for explanation. Okay? So much for having a non-statistical mind, right? Okay, let me wrap up. Just to show you, just to say, don't forget how it started this. I proposed to you that we were trying to make sense of Meyer's claim that Darwin, what his great innovation was, he introduced population thinking into biology. And one sense of this seems to be clear. In a metaphysical sense, he did introduce this idea of species not as essential qualities. That's right. But the entire literature, most of the literature, hopefully until now, also has a sense of methodological sense of population thinking, where statistical thinking is really the pinnacle of population thinking, and the old idea is that Darwin wasn't one of those at all. But I hope he convinced you otherwise. So much for having a non-statistical mind. Okay, I'm done. Thank you.